Imagine holding physical proof of how the universe actually works, but knowing that speaking it aloud could cost you your freedom. For hundreds of years, human understanding relied on the geocentric model, the absolute certainty that Earth stood perfectly still while everything else in the sky rotated around us. The authorities of the era tied their power directly to this model. A stationary Earth meant a stable, unmoving center of creation, making this specific planetary layout a legally enforced matter of faith. But as astronomers tracked the stars year after year, the mathematical paths didn't quite line up. The data was messy, requiring complex calculations just to make the old model function on paper. Equations alone rarely overturn entrenched beliefs. To dismantle a legal and cultural mandate of that size, someone had to present undeniable physical evidence. In 1609, word spread of an optical device from the Netherlands. Galileo took the basic design and engineered a more powerful, refined version. This diagram shows his refracting telescope's mechanics. Parallel light waves enter the objective lens, which bends them inward. Before they cross, a smaller eyepiece intercepts the light, bending it back into straight lines, projecting an immensely magnified image directly into the viewer's eye. Pointing his instrument upward, Galileo mapped the moon. He documented massive craters and jagged mountains, casting long shadows across its surface. The prevailing dogma insisted celestial bodies were perfectly smooth, divine orbs. These jagged ridges proved the objects above Earth were physical, measurable terrain. Turning his focus to Jupiter, Galileo tracked 4 distinct points of light moving back and forth across the planet over several nights. They were large moons, trapped in their own orbit. Jupiter's moons provided the first visual confirmation that celestial bodies could orbit something other than the Earth. This sequence shows Venus shifting through phases of light and shadow. Venus appears as a small, full disk when far away, and a large, thin crescent when close to Earth. This specific geometry is only possible if Venus circles the Sun rather than Earth. Armed with physical measurements rather than ancient philosophy, Galileo published his findings and publicly endorsed the heliocentric, or sun-centered, model of the solar system. He pitted the raw, verifiable output of an engineered tool directly against the most powerful institutional belief system in Europe. The authorities responded quickly, treating this contradictory evidence as an explicit challenge to the laws governing their society. Galileo was summoned, put on trial, and ordered under threat of torture to formally retract his observations. He lived out his days under house arrest. The suppression halted his publications, but the observational standard was out in the open. The scientific method shifted permanently from assuming how the world worked based on old texts to physically observing and measuring it. Galileo mapped the actual motions of the planets, yet the mechanism holding them in those paths remained a mystery. He had exposed the geometry. The physics came next. Decades later, Isaac Newton noticed an apple detaching from a branch and accelerating to the ground. He asked a simple question: why do objects consistently fall in a straight line toward the center of the Earth? Newton calculated that the same invisible force pulling the apple downward was reaching out into space, anchoring the moons and planets to their respective stars. This visualization shows the universal law of gravitation. Every mass in the universe pulls on every other mass. This mathematical mechanism was the engine driving the very heliocentric solar system Galileo had observed. By engineering a lens and demanding that humanity look closely at the night sky, Galileo surrendered his own freedom. In doing so, he provided the exact observational data that anchored humanity's true place in the cosmos.